We're here once again with the Cycle World podcast. I'm Mark Hoyer. I'm the editor-in-chief. I'm with Kevin Cameron, our technical editor. Today's topic, inside the hot room. This is everything about the combustion chamber, our striving to get a homogeneous charge of gasoline and air, most specifically oxygen.
Yes.
That's the part we care about. That stupid nitrogen, get rid of it.
It's there to keep the lid on.
Yeah, that's good.
If we breathe pure oxygen, bad
Not
things
good.
happen. Yeah.
Not good. But yeah, everything that's happening with a combustion engine, of course, we need good combustion. We want a homogeneous charge. We want everything to be perfectly mixed. And within some confines, what we're looking for is perfectly complete combustion, because we'd end up with water and carbon dioxide.
Yeah. That's when it's complete.
If it's perfectly complete, that's what we want.
Yes.
Yeah, that would be great if we could do that. We're striving for that. We'll talk about, ways that we reduce hydrocarbons and other things about the combustion chamber, because the combustion chamber, would you say the combustion chamber extends from the top of the top ring to the lid of the chamber? So
clear around to the other side. Yeah.
This stuff, we're going to talk about that. So thoroughly complete combustion, and within the confines of the crank rotation, combustion as short as we can practically make it.
Yeah. Because the longer hot gas sits against comparatively cool metal, the more of the energy in that hot gas will be lost as heat to the cooling system.
Right.
Whether that be fins or water.
Yeah, that's a great point. We want to keep the heat in the chamber and not have it transfer out through the engine. And this reminds me of a story of early drag engines. The iron drag engines were faster than the ones with the aluminum heads.
Yeah.
Because iron wasn't transferring heat out of the chamber as quickly. So in that short duration where you didn't have to, like on an air-cooled racing motorcycle where you had to make a great big heavy cylinder head to be the repository for all the heat that you were getting on the front straight, and then roll off, let it cool, get rid of some of that. In a drag car, you're just like, it's cold, let's go. And then and you're done. So the iron ones were for a period of time until the advantages of aluminum could be exploited. We're faster. So you want to keep the heat in the chamber. If you could keep all the heat in the chamber, man, is that 100% efficiency? Close?
Well, because there's all sorts of things in nature that are constantly nibbling away at perfection. And we wear pointed shoes when we walk around in the combustion chamber to deal with those little critters. Well, in 1862, while the U.S. Civil War raged, and brother versus brother.
Kevin, I love how it goes back to 1862.
A Frenchman named Beau de Rochat came up with the four-stroke concept, and he got so many things right. He said that the combustion chamber must have the smallest possible surface area, which we were just talking about. We want to lose as little heat from combustion as possible.
So he says this in 1862, and how come we blow it so hard over and over again? Like, how do we screw that up?
Because when we get in, the internal combustion engine is already there, and there's already a stack of little cards with sticks glued to them with all the right answers on them. So they hold them up, and we memorize them. Here's another. And only by going back to first principles do you say, oh, wait a minute, I get it now. So Beau de Rochat he's not given credit for inventing the four-stroke cycle, because Otto and Langen really made it work in the late 1870s. But the greatest possible peak pressure from combustion, that was another of Beau de Rochat's ideas. And once you've heated the gas above the piston, you must expand it as far as it can still give meaningful work to the crankshaft. Well, terrible fuels fixed it so that the early Model T Fords had a 3-to-1 compression ratio. So it had this huge combustion chamber, lots of surface area, but gasoline was cheap in 1915. So it all worked out. Along came Otto and Langen in 1878 with the four-stroke concept. And interestingly enough, the idea of overhead valves was a Russian invention. Boris Lutsky in 1888 came up with a combustion chamber that was a cone, had an intake valve at the top, and a exhaust valve at the top, and an intake valve at the side. But very quickly, all those ferociously creative inventors in France, where the seed first took hold and grew fast, internal combustion mania, every conceivable combustion chamber shape was created. This was especially easy because the combustion chambers, as I've said, were large because the compression ratio was low. In modern engines, if you want a 13-to-1 compression ratio, you can't have a lot of valve overlap. That is, the valves, intake and exhaust, both being somewhat open at top dead center, because you've got to cut clearance for those valves at that lift into the piston. Yes, plus a safety margin. We don't run anything down to zero.
No.
And so...
I mean, see, the safety margin he's talking about is how close is the squish area of the piston, which is this band on the edge,
to the head.
How close does it come to the head?
And how close do the valves come to the piston?
Yeah, but this is all dynamic, right? There's a little bit of, it might be steel, but
it's expanding and contracting.
Expanding and contraction with heat, and then when you're spinning everything at really high RPM, how many psi of pressure are we exerting on the rod? And there's just a lot going on. So we street guys are like, hey, 40 thou of squish is a good place to stay, and then some of the fancy people will get it down to 28 thou or something.
Yeah.
Really on edge.
So Boris Lutsky is one of those overlooked names. He went to work for MAN in Germany, a diesel company. Around 1903, a whole bunch of different things happened. Mechanically operated intake valves. Up to that point, they'd been atmospheric. In our podcast about Glenn Curtis, we talked about his early engines having intake valves that were pushed open by atmospheric pressure. The piston creates a partial vacuum in the chamber. The intake valve with a weak spring on it, air rushes in. And so 1903 was also the year in which the side valve engine became prominent. Lots of them were built thereafter. A side valve engine has the intake and exhaust valves, stems pointing downward next to the piston, not above it, as in overhead
in the block. Yeah, in the block next to the piston. And it's nice because you just have the tappet and the valve and the spring, and it's all this kind of like relatively compact little guy.
Yep.
And it just sits right there on the camshaft, and
hard to float those lightweight parts.
Yep. And then the air goes in, but it has to go like this into the chamber and then into the piston.
Down to follow the piston. Sure.
Yeah.
Well, Lutsky pointed out that having the valves in the head meant that the airflow was nearly straight. Ooh. In through the intake, following directly the piston on its
Once
suction
again,
stroke.
I looked at a 37 Rolls-Royce small horsepower inline 6-cylinder.
Yeah.
The small horsepower, the large horsepower cars were the V12s, Phantoms, and all that. And then this was called the 2025, which was like the horsepower rating for taxes in England. And it was an inline 6. It had a carburetor, an updraft carburetor on one side of the block, and it pulled the air up and went through the block and then into the intake manifold and into the engine. I mean,
Wonder
that's
it
a
didn't
long
get lost.
that's a long trip, and I don't know what it revved to, but and you had spark control and mixture control on the steering. That's all I wanted it for, was
Yeah.
to be in. I wanted to get rid of those stupid rider aids. Who
Well, the
needs
side
automatic?
valve, yeah, side valve was very popular because it was simple. If you want to make an overhead valve, how are you going to lubricate the rocker arms and the valves, the push rod ends?
And to be fair,
Well,
and you pointed out, compression wasn't a big deal. So having a long chamber like that was like, who cares,
yes, the side valve chamber extended out over the valves that were next to the
Yeah,
piston.
so
So it,
we're in a nice little round zone, but if the valves aren't on top of this circle and they're over here, that means the combustion chamber extends out.
yeah, more shaped like a wide shoe.
Yeah, with two big
So
toes.
uh, fuel really didn't get understood very well until the mid 1920s. But the concept of squish is usually attributed to Harry Ricardo, who patented it in around 1920 in England. He licensed the patent to Harley Davidson, Ricardo heads.
Two things with
Uh,
that. Very good marketing, my friend. Way to take the idea and do something to put your name on it, and also cha-ching. Made a buck.
the idea of squish is, and you can see how this would be easy to implement in a flathead, in a side valve engine. The piston comes up, and you've located some part of the cylinder head quite close to the top of the piston at TDC. So as the piston arrives at TDC, the air between it and the squish zone on the cylinder head goes, whoosh, it is squished out into the chamber above the valves where it creates turbulent motion. This is what makes combustion move fast.
And that's why we have this piston, and the spark plug is in the middle of the valves. And so
Yep,
this ring all the way around the edge squishes it all and concentrates it, also mixing it up, giving it lots of turbulence,
yep.
and then it gets lit right in the middle, and it's nice and compact in this area, and bang, and away we go. And this is out of a probably 12-to-1 engine, and our 1300 GSA is 13-to-1, I believe, or more.
Mm.
Even the R12 G/S, an air oil cooled flat twin, they have pushed that, I believe, to 12 or 13-to-1.
Yeah.
Through other, there's lots of hocus pocus going on, but yeah, so that's the squish, and that's what we want: mixing, and then concentration around.
Now, this
Spark.
concept of squish was invented at least 4 times. Piquet et Moquin Company in Geneva is one inventor. They didn't bother to patent it. It worked for them. Another inventor was Walter Moore, who later designed Norton's CS1, Camshaft 1,
yeah.
their first overhead cam engine, which later became the celebrated Manx Norton road racer.
Venerated, too.
Venerated, yes, indeed. And Charles Franklin, the Irishman who became a self-made racing success at the Great Brooklyn Speedway in England, and was then made chief engineer of Indian in the USA. He invented squish sort of by accident. Walter Moore, too. They had a new 4-horsepower Douglas, and they took it to the test hill at Brooklyn Speedway, and it would not go up the hill. It just started knocking immediately and quit running. So Walter Moore wasn't going to take any nonsense from reality. So he took a brand new casting. The cylinder head and the cylinder were cast in one piece, sawed it in half, and looked at the geometry. And he went to the foundry department. He said, "Boys, I'm sending out," in those days it wasn't for pizza, "for dinner, and we're going to be here all night." And they made a number of different changes to this shape, and he came up with a shape that seemed to run particularly well, and today we would call it squish.
I wonder what they all called it. I wonder if they had a name for it, because typically what happens in academic circles is like I don't know, in the areas of philosophy, they make an entire career on just changing the language. You get
Yeah.
it. It's kind of the same thing. We're talking about the same topic, but somebody comes up with, like, Michael Foucault had this, like, no, was it Derrida? Had this concept of deference, and it was like the difference between, I mean, I love philosophy because this is endless,
So academic.
endless noodling. It has no consequence.
How are we going to choose the main jet? Probably not Derrida.
Yeah, exactly. It's
Anyway,
sort of it's a weird relief.
anyway,
Yeah.
the reason I go on about this multiple invention of squish is that at the beginning of any new technology, there are a lot of people working on it. They haven't decided the best way to do it yet, and everyone's hoping to hit it right. And so, at least 4 inventors of squish. And during the 1920s and 30s, side valve engines were noted for their good pulling power from low speed. Why was that? Because squish gave a vigorous stir to the fuel air mixture so that when it was ignited, it burned rapidly, too fast for the chemical process that lead to knock to take place. Meanwhile, the overhead valve engines, such as the 8-valve Indian board track racer and Harley's 8-valve, they were good on top end. But if you pulled the engine down to low speed, oh, naka, naka, naka.
If only they
So,
had, yeah, if only they
yeah.
had good squish, right?
So, but the compression ratio was so low that the piston was never anywhere near the head in those early engines. So people weren't thinking, how can we transpose squish from a side valve to an overhead valve? And Charles
So
Franklin's, yeah,
we were getting turbulence without needing it to happen only because of velocity. Right?
yeah, because there's a lot of velocity in the intake process, especially once you realize there's an advantage in high speed intake. Anyway, Charles Franklin's side valve Indians, based on the Power Plus engine, often won races against the 8-valve overheads. How could that possibly be? Squish is how. So,
and how misleading that was for so long,
yeah,
because we didn't have the answer that took us to where we are today. We didn't have DFV
to look at. Ooh.
Yeah, wouldn't that be great? Could you imagine taking a DFV Cosworth back in time and just secretly applying that to the metallurgy that was available, and
have a look at this, fellas.
walking out of a shed and going to Brooklyn's and just kicking ass?
Yeah.
That's I think the basis of every time travel movie is that kind of all-knowing power, right? That gives us.
Yes.
Yeah.
And that's the basis of vintage racing. Because you do know now what you should have known then.
Well, it's really true. You go out to ARMA and you look at the bikes that are competing in 500 Premier or whatever, the 500 class where you get Manxes and all that stuff. Nobody's really winning on a truly vintage Manx.
No.
It's all remade. The G50.
And they're turning 9,000 RPM.
Yeah, they're kind of scratch built, and they've got electronic ignitions, and there's just many pieces of that new metallurgy, new parts.
All the good stuff.
It's all due respect to Team Obsolete for showing up with stuff that's actually vintage and got magnetos, but
and what Robert Iannucci says is that so often they've been able to win races using the standard stuff because it was so optimized at the time. It worked well. Anyway,
just not as often.
Yeah. From the middle 1920s through the 30s, fuel octane number, its resistance to knock, was steadily improving. And in order to live right on detonation's doorstep, they raised the compression ratio with each improvement in fuel quality. And when you raise the compression, that is, make the combustion chamber smaller, you create a higher peak pressure, and you also have a higher expansion ratio. 10-to-1 compression is also 10-to-1 expansion. So what this was doing is it was moving the cylinder head closer to the piston. Sooner or later, somebody's going to say, now that the cylinder head is so close to the piston, maybe we could create squish between the two. And that somebody was Leo Kuzmicki, who escaped from Poland during World War II on a magnificent odyssey, which is not the subject of our podcast, and ended up sweeping the floor at Norton Motors. And he and Norton's race director got to talking. And the result of this was maybe this idea of bringing parts of the piston close to the head could work in an overhead valve engine. This is strange because Joe Craig, who was in charge of racing at Norton and virtually ran the company, he sucked up their whole R&D budget, which is why they kept on making singles when other companies were, well, Triumph was raking it in with the parallel twin. Nortons were sort of stuck in the mud until 1947. But when at Norton they decided to build a squish piston, they solved two problems. Well, I won't say solved. They ameliorated two problems. First of all, to get high compression, 10.5, say,
should we call it this research and amelioration?
Yes.
Instead of R&D.
I've often wished to be ameliorated. In any case, here's this piston dome, and it's sticking up there. But you can't create squish in the center of the head. You can only do it around the edges. So we get to take that material, lower it in the middle, and raise it up to the points where there aren't valves to where it can nearly touch the cylinder head. What this did at first was it removed the obstruction of the piston dome to a considerable extent so that the rapid motion of the intake entering the cylinder head created a tempest in a teacup. Lots of turbulence. As the piston rises, when you've got that terrible piston dome on there, the turbulence is sort of, I quit. Nice one. That's a better one than the steeple, church steeple type.
Yeah.
So when they made the squish piston, they picked up horsepower and torque.
Oh, thank goodness.
And it's been squish ever since. Now, the combustion chamber, as I said earlier, originally there was such a variety. There were engines that had 3 exhausts on one side with their stems pointing down, 3 more exhausts on the other side, and a huge intake valve in the head. Any concept you can think up, they tried it. And to extend the combustion chamber out over these side-located valves meant that there could be crevices, nooks and crannies, as a certain brand of English muffin calls it, in which flame could persist after the combustion process, so that when the next fresh charge was compressed, it would go off prematurely or otherwise at the wrong time. This at the time was called misfiring, meaning firing when we don't want it to. Firing badly. And
I was talking to an engineer, and they were talking about the combustion chamber shape, etc., and ignition or injection timing, and which way the injector was pointed. Because if your instinct is let's fire it into the cylinder directly with the charge, but in fact that can keep it from mixing. but it's also one reason the shower head injectors were extremely long distances, so that at high RPM it had time to atomize, and they were just sitting in the airbox. But you could point the injector sideways to the flow and get it to tumble. But he said the goal was reduced cycle to cycle variation. And I thought, well,
cycle to cycle variation.
That's a nice way to, that's a nice academic way to put, yeah, she's running good. So.
The thing is with cyclic variation, if you could take the very best cycle that you've recorded on your combustion chamber microphone system and make the engine run like that all the time, you might gain 20%. And it might even be with improved fuel consumption.
I need that on my 460.
Bobby Strawman, who was the champion man for so many years,
I've seen all
at the
pictures
races
with his little monocle, the little magnifier, and
yes, peering at your spark plug.
Looking
well,
deep.
I think you could go up with the ignition advance a quarter of a degree. You can see a quarter of a degree on the spark plug.
I wish we could get inside of here. This would be a hard one to read, but probably okay. Long little electrode positive. You know, I'd say most of us who are still looking at this, because nobody looks at these anymore. All you're doing is looking at your lambda and all that.
They're unseen. Yeah.
You don't have to use this anymore.
We have oxygen sensors.
Yep, oxygen sensors, others, pressure, temperature. We're going for it. But it's cocoa brown. He's like, light brown, cocoa brown, and that's where a lot of people's spark plug reading begins and ends. But it's actually all those little rings that are down here on the center electrode, and how's it coming out on the negative. This is sort of a bad example because it's a twin.
But this is like tricks to make the linotype work faster.
Yeah, exactly.
We don't use linotype machines anymore.
Yeah. Well, we do in ARMA.
Yeah, sure. Well, the 2-valve, 4-valve thing. In the 1920s, the 4-valve engines of World War I aircraft engines were complicated. They weren't necessarily unreliable, but the more parts you have, the more failures you can potentially experience. And at Fiat, they came up with the idea of putting 2 valves above the piston and allowing them to be very large by angling them apart so that they were on the long diagonal rather than having to fit inside the bore circle. And that was the ruling paradigm in combustion chamber design from 1923 until the early 1950s.
But even then, the Jaguar XK engine that they used in, the XK 120, 140, 150 E-types, and pretty much everything that they made until they made the V12, that engine persisted. The XK engine persisted until 87, 88, 89, 90, somewhere in that range when they came out with the double overhead cam version. They were still using that. And it's the chamber that you described. This is a piston from a Jaguar, hemispherical head, and the cams are out. I forget the included angle of the valves, but the cams are tuned way out.
Yep.
And they made it work. Although they do detonate at 1800. That's a very susceptible RPM.
A bad time.
Yeah, you got to.
So 90 to 96 degrees included angle. This was fine when compression ratio was low because you could have that big hemispherical combustion chamber. That and the flat top piston worked out just fine. 5-to-1 compression, we're good. But when the fuel octane began to improve as the chemists and the engine people began to cooperate and understand each other's problems, they began to push detonation away. And
all hail leaded 110, folks.
You got it. So this 2-valve thing, when the fuel octane got better and the compression ratio rose from 5 to over 10 by 1939, then you had this tremendous piston dome sticking up into the combustion chamber, both of which had a large surface area, violating Beau de Rochat's first principle: smallest possible surface area in the combustion chamber. And it wasn't that Keith Duckworth was thinking of Beau de Rochat. He was simply dealing with the problems that were in front of him.
Frank Costin.
Yes,
Keith
the
Duckworth.
chassis man.
Frank Costin, Keith Duckworth, Cosworth.
Joined to make Cosworth, yes.
And Cosworth, as we've said many times, I just want to put the stamp on it that, Cosworth really did it. Cosworth built the combustion chamber 4-valve head.
That everything has nowadays.
We're all...
There's a little step along the way in the middle 1960s when Honda re-adopted 4 valves per cylinder, not because it flowed so well, but because those little tiny valves were so much easier to control at very high RPM, up to and including 21,500 for the 1965 RC 115 50cc twin. And so 4 valves came back into automotive use and then into motorcycle use, but still with the large valve included angle. And Duckworth moved forward by increments in his thinking, and what he ended up with was a bore that was about 1.3 times the stroke, so a fairly large bore, with 4 valves with their stems at a 32-degree included angle. So the chamber is now like a shaving off of a hockey puck. And instead of having squish to generate all of the turbulence, he decided to compromise on the uses of the intake flow. If they tipped the intake port up so that it aimed down at the piston, cylinder filling was best. If they had it at a lower angle, it flowed across, hit the other cylinder wall, and formed a barrel motion. That's what Duckworth called it at first. Today we call it tumble.
Tumble.
And it's a way of storing intake energy in the cylinder so that as the piston rises, it's like the skater who draws his or her arms to the chest and spins faster and faster. So what happened when the Cosworth V8 of 1967 went up against the French engine, which had much more valve area? And in those days, if you read the books that we've all read, if we're
was that a
mad
Matra?
Enthusiast, the Matra V12.
Legendary sound.
Yes. Well, we love 12 cylinders. No question about that. The little V8 just left that V12 behind. What was going on? The V12 had a slower burning combustion chamber. It had a lot of combustion chamber surface area. Beau de Rochat, are you listening? And so heat that should have been driving the rear wheels of those Matra racing cars was driving the radiator. And in the Cosworth V8 DFV, that heat was indeed driving the rear wheels. And it took a couple of years for the competitors to kind of, what are these guys doing? How are they getting these unreal results? And that 4-valve flat turbulent combustion chamber using Tumble is the world standard now for combustion chambers for cars, light trucks, motorcycles, because it works. It's best for racing and it's best for grocery getting because it puts everything in a reasonable place. it burns quickly, so it doesn't waste fuel, and it's just an all-around winner. And that pretty much concludes the combustion chamber story, except for the fact that now, um, with the aid of electronics, we no longer are relying on ignition that comes at a fixed point. For example, if you have an old parallel twin Triumph, say a 65 Bonneville.
Well, I know people are thirsty by now, so what I want to say is Velocette.
Okay.
And I'll use the Velocette BTH Magneto as an example. You were going to,
I was going to say
I'm hopefully saying what you're going to say.
Yeah.
Is mine has an automatic timing device, but it's sort of the same if you're doing the manual timing device, which in the old days on a Magneto, you would move the lever and change your timing. So when you set your timing, you'd set it at max advance because that's what was important. And you'd set it at 36 or 40 or whatever the book was asking for. And then when you went to start it so that it didn't backfire and throw your leg through your chin, you would turn it to the starting retard. You retard it. And it's 10 degrees before top dead center or 5 degrees instead of 40.
Yep.
And it did, so anyway, because you can't kick it hard enough to get past compression and do all of that with enough momentum to get it to go over and start because it's happening too soon. And that's why it kicks back and goes kapang and then ow. And then, but if you take it back to 5 degrees, you can, and you have time and then dip. And then you can mess with the timing a little bit and get the nice idle that you're looking for. But as soon as you roll away, you're turning the timing to advanced. You're giving it max timing. The ignition on the Velocette, another drink, is an automatic timing device, and it has springs and weights, and pretty much it's not much of a curve. It comes all in at a certain RPM. It happens fairly quickly.
Like 1200,
Yeah, even with fresh springs, even the 1995 Ducati 900 SS with Kokusan ignition modules, all they did, just like a 1975 Laverda with an early Bosch electronic system, it's practically a switch.
Yeah.
It has an idle RPM, and on the Kokusan, I want to say it's like 2,700, 2,200. It goes from 10, I can't remember, sorry if this is wrong, Ducatisti, but it's 10, and then say it's 36. It doesn't go, it goes, Hee! I mean, in an RPM range, it's like 100.
It's a step function.
It goes from 10 to 36. That's why when you're on choke with a standard ignition on a 95 Ducati, it's like, and you're like, no, less choke, and it stalls because it doesn't have timing to run where you want it to. Yeah. And I spent, I don't know how many hours on the dyno with my Laverda, 75 Laverda triple 1000. I had bought a new pipe for it because the stock lock Franconi had a collector that was the size of a pencil.
Yes.
And this is 1,000, and it's making, and it was quiet. They were trying to quiet them down. It was making like a 54 horsepower or something like that, which is about what a Commando would make, a good running Commando. And I'm like, dang, this doesn't seem right. So I got the Kian exhaust system, which was a stainless system made in England, cost a fortune. But I put that thing on and I started rejetting the carburetors. And I was going up and down the street to Ron Wood, on the needle exchange, because Ron Wood Racing was doing all the Del Ordos for the flat track guys and people who were using them at that time. And that's what the Laverda had. And I was on the needle exchange program, and I am detail oriented, and I have an ability to concentrate on things a lot of people find very tedious, but you think about it a lot. It's just a trait, it's a trait, and it comes about sometimes when I'm cooking, and even I focus too much and I'm not having enough fun. But I got the jetting, what I thought was really good, but I couldn't get rid of the stumble. There was this stumble, and I would hold, and the dyno's nice because you can just stand next to the motorcycle and do things with the throttle and listen to it. You're not, no helmet, none of the, no traffic. And so you're just running it on our Dynojet 250. It's right there in the other room. You're just running it. And I couldn't get rid of the stumble, and I forget the RPM, but it was around 3,000. And I mean, I had done it, man. They were synchronized like crazy. I put a straight edge across the top of the carburetors because they were metal mounted and you could kind of rotate them. And it was all on cables. Yeah. So they're not racked. That meant that, let's make them perfectly straight. So I got my machinist edge, and put that on there, and I did all of that work, and I got exactly the right needle, and I got the right slides with the right cutaway and the right damn accelerator pump ramp, because there's a
Yep.
ramp on them that kicks the accelerator pump. So there's a lot going on, and I worked it, and it was running great. And I'm like, I could not get rid of the stumble. I tried, okay, we'll go to smaller pilots, and you know, and I burned a lot of brain cells, and I just, I had to hit the reset button, and I did reading, and I read and I read and I read, and I finally found an instance where the Bosch electronic ignition was explained.
Yeah.
And it said it holds 10 degrees or whatever, I'm guessing it holds 10 degrees until 3000 when it switches to 35. And I was on the dyno going, and I'm getting like a little, I'm like, what is that?
So
Sorry. Big aside.
Today's ignition boxes have optimized timing, minimum for best torque, MBT, that has been determined on the dyno with standard units. And that is stored as an ignition map in the ECU. And the engine does not breathe equally well across the whole power band. If the cylinder is quite well filled, the flame is going to spread more rapidly. The flame speed will be higher. In areas where negative wave arrives just as the intake valve is closing and sucks out some of what should be in there, it's going to need more ignition. So what modern ignitions do is they provide the timing that is best for that speed and that throttle opening. And that is all canned in the ECU.
And by the way, Czech company Ignitec makes a programmable ignition box that you can plug into your Ducati system, and then you can put a true curve in it. And you know what I mean, I got a lot of benefits out of that, a lot of low end smoothness, because now the timing is happening at a place that's optimal. Like what are you looking for at idle, say, when you're tuning? You're looking, the reason you change the mixture on a carbureted bike and even on a fuel injected bike is the RPM. You tune a carburetor idle mixture screw to get the highest RPM. What is the highest RPM? It's the most horsepower.
Yes.
It's
a maximum power mixture that you're looking for.
You're looking for the maximum power mixture. That's what you're doing. The ideal spark timing could be 10, could be 14. You move it around, and you're going to not naturally, but anyway, you're looking for the maximum horsepower. And then now you can look for that everywhere across the curve. And the Ducati completely changed that low speed tractability from the Kokusan to the Ignitec, low speed tractability, ability to set the choke at 1800 without it either running away or stalling. It became a much different motorcycle. Sure. I never changed one in the Laverda, and Belisette, it's still mechanical advanced, but you can put a BTH replacement electronic ignition on those, hide your battery, and if you don't want to, people talk about the unreliable magneto and they're going to replace it with the electronic ignition. And I say, you realize that magneto is 50 to 80 years old or more, 100.
Yeah, could be 100.
Just
well, here's the last problem for combustion chambers, and that is we want to be able to have good performance on top end, but we want to have very high compression for acceleration. Now, acceleration just means performance below top end with the engine accelerating. And compression ratio, the highest usable compression ratio, HUCR, is what we'll use if we have electronic means to prevent disaster. And this is why modern engines such as 1300 GS from BMW have knock sensors. If the engine begins to knock, it retards the spark a little bit and then tries again. Oh, he's got a bad tank full of gas. Well, we'll have to sort of hover down here. But once you're protected against detonation, you can go way up with compression ratio without disaster. And that's what manufacturers have done. 13.3, 13.5 to 1. Those numbers were just madness 20 years ago.
I haven't looked recently, but I have searched in the past for essentially an aftermarket knock sensor that I could hook up to an ECU and control spark on vintage engines, just so that
you wear a stethoscope and keep your thumb near the spark lever.
Push the screwdriver on there and stick your ear on it.
That's the one.
Works good. Long screwdriver, folks. It's pretty
so
good.
Now we've raised the compression ratio, so the piston is very close to the head. What does this do? It kills charge motion. It kills turbulence. It slows down combustion. Well, we go in there and we round any sharp edges like the edges of the valve clearance cutaways. We smooth them out. We do everything we can to prevent energy loss from this mixture that's turbulating around inside there. But we find that it really isn't good enough. So at some point, for example, if you're racing, if you're going to a track that features a lot of acceleration, you run the high compression, knowing that, yes, you'll lose on top end because the turbulence won't be there to support the fast combustion. It's a worthwhile sacrifice because you'll win on the acceleration much more than you lose on top end. And there have been engines that were very much this either or way. But to create an engine that can do it all is quite an achievement. And this is one of the areas in which it almost seems as if Euro 5 is cooperating with engine designers, because Euro 5 says, well, we want to cut down on unburned hydrocarbons, so we don't want the intake and the exhaust valves open simultaneously more than just a little bit. Well, you're thinking to yourself, that means we can make the valve clearance cutouts in the piston crown shallower. That will help to raise compression. So now we can move the piston away from the head a little bit for the same compression. Another thing that happens, of course, and I talked to Claudio Domenicali, who's now the CEO of Ducati, about this years ago. He said, often we have to go to excessive ignition lead to burn very large bore engines with short strokes because that combustion chamber is so slow burning. So that compromise remains. There is no way to have it all, but you can slant the compromise in whatever direction you need to go. So another sideline is that the United States Army used a lot of diesel engines. And naturally, those diesel engines require a long supply train back to a ship somewhere tied up at a pier. They're loading barrels of fuel onto trucks, and the trucks are grinding their way through Pakistan and into Afghanistan, just to give an example. So it would be a good idea if the engines used less fuel. What if we made an engine whose combustion chambers stayed at a very high temperature the whole time? Heat loss is proportional to the temperature difference between the hot thing and the cold thing. This is called delta T, delta meaning a small change in. Delta T rules. The Army put a lot of research into designing what they called an adiabatic engine, one which neither gains nor loses heat through the vessel. And they found they couldn't do it. They found that the turbocharger energy, which comes from the exhaust and creates some back pressure, required to push hot air, to push any air into such a hot combustion chamber the air immediately heated and said, I'm not going in there.
Right.
No way. And so it expanded.
Yeah.
And you're trying to compress air whose temperature is rising. A fool's game. And so they gave up on the adiabatic engine. But subtle people in the engine business, like Rob Muzzy, for example, or the people at Ducati, Gigi Mengele, are thinking about these basics that go back to Beau de Rocha. And they are trying A, trying B, trying C, so that combustion chamber design continues to evolve. Now you'll notice that automobile engines are going back to bore and stroke approximately equal, or even that strokes are now in some engines longer than the bore. That's a many-sided sort of change. On the one hand, you're making the combustion chamber smaller, reduces heat loss. That's good for economy. It's good for carbon reduction. You don't use as much fuel, you don't spew out as much carbon dioxide. And also, of course, the piston ring crevice in a big bore. It's a long way around a 4-inch piston, but a 3-inch piston, it's only 3/4 as far.
So yeah,
And
let's pause
that's
there.
where unburned hydrocarbons are coming from.
So what he's talking about is, here's the piston. You can see the top ring is here, and the crevice is this amount of piston to the top of this ring. So there's air fuel mixture coming here, because as soon as it lights, the pressure goes up, and these piston rings are designed to be essentially inflated by the pressure. And so the pressure goes in behind the ring and blows the ring out against the cylinder, and then you have that crevice. If you look at the top land on this, it's a little bit farther. The rings are thicker. These have a higher friction ring, but that distance is farther, and that would hold more hydrocarbons. And then if you make the bore this big, 1/6 and 1/8 versus this, which is probably 85 or something, 82. Yeah, this is a lot more crevice, right? Look at the distance there. So B25, lots of rings, lots of friction. Sorry, Spotify. I just showed you some pistons. We used props. Occasionally we use pictures. So one of the things that came to mind is that we've talked about tumble, we talked about barrel motion in the DFV, but we skipped how 2 valves were doing that kind of.
Yes, so we did. And the funny thing is, the English went with it, and the Italians, with the exception of Dr. Taglioni, ignored it. So here we have the bore, and here's the intake port and the intake valve. If that's what we have, the air goes in symmetrically. You get no rotation of the air one way or the other. So
basically what he's saying is the port comes in perpendicular to the cylinder. It's
right.
Coming in.
But if we move the port off to one side, it's like the game we play, filling a bucket with a hose. You can make the water swirl to the right, you can make it swirl to the left, you can make it stop by using the velocity of the water coming from the hose to make the water, in our case, the fuel air charge, spin. That is a way to store intake energy above the piston that may make it to the ignition point, so that that turbulence will accelerate the flame speed, because it shreds the flame kernel created in the spark plug and carries the shreds quickly to all parts of the chamber, causing a rapid pressure rise.
Exponential flame propagation, man.
Yeah.
Everybody's shaking hands, as you said. More people doing it, faster the disease spreads. So this is the piston, but we'll call it the chamber. And here's my pencil pointing to the center. If that's the intake, then the air is going this way. It's hitting this big knob in the middle, not doing its thing. But if you just go kick it to the side, here's the hose at the side of the bucket, and it's whipping around and tumbling and doing its thing. And
Yep,
those offset ports, you find them all over.
you
It's
certainly
great.
do.
It's great. And so you don't
So,
need. Well,
no,
here's. I would like to bring up the Norton Commando because
sure.
it's a great example of a two valve that's doing a lot of things right. So overhead cam, 4 valves per cylinder is definitely where we are. It's definitely superior. But this parallel twin designed putting 40, 38, 9, the essential beginnings of the Norton twin.
1947.
47.
Yeah,
It ran great, and the ignition timing, the max timing on a Norton Commando is 28 degrees. That's
quick.
very quick. I know you're thirsty. Velocette, you take a Velocette, very typical hemispherical combustion chamber, 2 valve. Spec is somewhere in the 38-degree range. Can't do that with the fuel we have, like the 91 that we have here. You just can't do that. That's why I love leaded 110. You put that in, you can do whatever you want with the time and get
Yes, sir.
optimal good times. But yeah, so
And
you can.
that is why in classical times, when Grand Prix racing teams had no idea what fuel would be the official fuel in Spain, in Italy, wherever they were running the next GP, teams that were wise carried a drum of toluene, which has a good anti-knock octane number, and they would just add 10%, 20% to the official brew, and
Moderately
away.
less, yeah, moderately less bad for you than tetraethyl lead, so that's good.
Yeah,
Great solvent. It's usually a big part of your carb cleaners and stuff. It's a great solvent. So
and it's not available during wartime because they need the toluene to make trinitrotoluene, which is TNT, a high explosive. So these engine things that we've been working on, they're not at the end point yet. New ideas keep coming along. And just the other day, I saw that somebody is making a rotating sleeve diesel engine
yes,
because they
sleeve valve.
found that most of the piston ring friction occurs within a few millimeters of top and bottom dead center, where the rings are not moving for long enough for the oil between them and the cylinder wall to squeeze out. So there is not metal to metal contact, maybe, but certainly metal to oil additive contact, which causes a friction coefficient that may be 10 to 100 times greater than an oil film.
Well, you do get a lot of zinc in the diesel oils, the
Yep.
ZDDP. So that's sort of the last line of defense, particularly on
Yes,
cams and so forth.
it is a solid lubricant that comes into action wherever there's high temperature,
I found out that
and
it's in that. Oh yeah, go ahead.
it's self healing as long as there's ZDDP, um, zinc dialpha alkyl di something. Anyway,
Phosphate.
as long as there's additive in the oil, it's self healing, and so there can be a polishing action
Right. So
because
it lays its little surface and then it's always there.
scrapes it off. Yeah.
Unless what I've found out recently that there's a high instance of calcium and I think another mineral, some of the detergents. And that's the interesting thing about diesel oil is it has the ZDDP you might want for a flat tabbed engine.
Yeah.
But it also has a very high detergent, which actually can work against the ZDDP to a little moderate.
Because preventing it from forming the coating in the first place.
Yeah, or even removing it.
So dispersants.
Yeah.
When you think people as old as I am, their doctors are constantly talking to them about stroke and dismal topics like that, and it's very much like the formation of terrible stuff in the oil. Oil can polymerize with oxygen to form gum and horrible sticky stuff.
Oh,
And
the old oils had a wax content in them.
Yes, that's really old, but they could wax up just like now. If you don't have an anti-wax agent in heating oil and your heating oil tank is cold, if it's outdoors, you may have to pour some kerosene in there in the winter to prevent it from waxing up on the filter.
Just build a fire under it.
But sludge and stroke are related because it's really the formation of sludge in your bloodstream, which is capable of occluding small blood vessels that may lead to intermediate algebra. Why can't I think of that anymore? I'm trying. And
I like it.
so dispersants, as they call them, coat the outside of any particles they find so they can't clump together, and they are taken out at the filter. When you change the filter, you're taking away the bad guys and putting them in a safe place away from your engine.
Nice.
So I think of changing the oil and filter. Oh, I have to do this. But we actually should do it cheerfully because we are triumphing over evil.
Well, and let's talk about evil, because part of that evil from the combustion chamber goes into your engine. And a really good combustion chamber, you would have an oil change interval of 5 or 10,000 miles, and the oil will remain nearly honey colored, or whatever color it was when it went in.
So lovely.
And again, I know you're thirsty, Velocette. So I ran my Velocette with various sort of standard pistons in, remanufactured, like new manufactured cast iron cylinders. I took my standard piston and my cast iron cylinder that I bought brand new, and I took them to the machine shop because I said, hey guys, I would like to see if these are roughly, just check the clearance first, 3.5, 4.5, 5.5, somewhere in that range, something. And also, is the cylinder round? And just bore gauges. I've never invested in bore gauges, so I don't have that. And I also wanted to get the cylinder surface scratched, basically. Like, let's put a nice cross hatch because it's iron. Yep. And I took it there and I went to pick it up, and he's like, yeah, the clearance is whatever it was, 4 thou, it's fine. And I said, is the cylinder round? And he says, well, it's round enough for your purposes. So I ran that, and it ran okay. It was a piston much like this Jaguar piston, ran okay. But, as I ran it, oil would get black in 1,500, 2,000 miles. Pretty dark. Yeah. It would get quite dark. And I didn't really understand why. I was just like, oh, yeah, the oil's dirty. I better change it. And I have a filter in it, in that bike. Well, I reverse restored that motorcycle. I cracked engine cases. I've written about it a million times, but I've cracked the engine cases. I measured the rod. This is the factory rod. Someone's pet, it's polished. It looks like a really great rod, except that it's bent and twisted. And in practical terms, it was unfixable. I tried to do V-blocks and pins and V-blocks next to the pin on the deck. And then, okay, it's not dropping into the V-blocks.
There's an illustration of this in Tuning for Speed.
And it's in a Harley book too.
Yeah.
Right.
Great.
And you just take a big bar and try to bend it so it's straight. And it was not practical to do that. So I went through the entire engine and I fixed a lot of things, and the crank is as perfect as a couple of different humans could work on it and everything. I used a Carrillo rod that was also perfect-ish, and put all that stuff back together. And then I did a Nicosil bore bored with a bore plate. Mm-hmm. And that bore plate squeezes what does it do? It simulates the compression of the material when you put the cylinder head in place. And on a Velocette, I think it's like 25 foot-pounds or 18 foot-pounds for the 4 studs, long studs that go from the engine case.
And remember, everything, all these solid-looking parts are elastic.
Very elastic, right? A steel tank, if you overpressure it, if it's a cylinder, with torus spherical heads, it'll balloon, and it'll stay. If you do it enough, it's stretched. It's really fluid. That's why hammer and dolly works, because you're you're peeling out the metal, you're squeezing it, you're stretching it, you're stretching the metal. So anyway, you bore it with this compression, and so that when you build the engine, the cylinder is therefore compressed, and the bore is as close to perfect that you can do with your boring bar. And this you Nicosil plate it like Millennium does Nicosil. You Nicosil plate it, nickel silicon carbide, very hard, very beautiful when it's done right. And you bore it and then put a plateau finish on it, which means you're knocking off the highest disparities.
Yeah.
And take a drink, folks. You're knocking. So if this is the point, you're knocking the top of the point off, but you're also leaving a reserve in the texture of the surface for oil. It's pretty cool.
Yep.
And so the point of all of this blah, blah is that you're making a perfect chamber. You're getting rings that go inside of there that fit that circular bore beautifully. And you have a very wonderful, I am a chamber, not a snob, but an elitist. I'm a chamber elitist. I want great sealing. And when I did all of that work to that Velocet, an air-cooled 1954 motorcycle, the oil stays clean practically forever. It doesn't change color because nothing.
Isn't that a son of a gun?
Nothing is getting by the rings. Virtually nothing. Very little is getting past the rings. And the chamber.
There we were at Monza in 1981 with a 250 TZ250H, and I thought, let's have a look at these rings. We had a stack of them from Yamaha. So one after another, I put them. This was a sunny day. I put them in the cylinder, squared them up with the piston, and held them up to the sun. Only about 6 of them I couldn't see light past the ring. How about that? We put 2 of the good ones in and gained RPM. So sealing is real.
Gaining RPM means he's making more horsepower, just to clarify.
Yeah.
And that's how a lot of racers will talk, especially 2-stroke racers, because you're not looking at a speedo, but I'm pulling 11,000 instead of 10.8 on the straightaway in 6th or whatever, and that's how you know you did it. That's a great.
And you add that little bit every lap. Say it's a 24-lap race. You have time to take several breaths of air, which means you could win, and those others would be toiling in your wake.
Yeah,
that's worth some effort.
Yeah, leak down. We could tell you, leak down's part of chamber. So when I raced that BMW last year at Barber, the owner Dan May, who's the executive director of ARMA, it's a BMW R75/5. We have a video you should go watch on Sega World's YouTube channel of me doing that. And that flat twin, he had the cylinders re-Nicosiled at Millennium. I don't know if he replaced the pistons, but certainly re-ringed it. Did the top end essentially before I raced it, and he showed me his leak down results of 0%, and I called BS. I was like, "No way!" And he's like, "No, I'm not messing around, man. 0% leak down, meaning nothing got out. You inflate the cylinder to a pressure, and then you measure the drop, and your fancy boys would be like, "Oh yeah, I got 3% or I got 5%." And if it's more than that, that's not good. You're kind of like, oh, I should freshen this up. 2-stroke, it's just like re-ring it, put a cylinder on it. I miss those days. I miss the
you want your engine to hold pressure like a scuba tank does.
And that's why that's why seating the rings, particularly in the old days when you had, you were putting a crosshatch on it, and you don't want to use your fancy low friction synthetic oils for break-in because you actually want the rings. You don't want a shadow, especially on a fat ring like these. You can run an engine. I had to take apart my Velocet so many times. Take a drink. I had to take apart that bike so many times. I got to look at the rings after certain runnings, and there would be shadows. So what you want is the whole ring to be perfectly shiny all the way around. So hold it up in the sun and look at the edges of the rings that are rubbing against the cylinder. You want it to be shiny and wonderful, mirror-like. And what I was getting was areas where they were gray. And if they're gray, they're not making contact.
Something's getting past.
And that's how your damn oil gets dirty. And it's also how the oil will make it past into the chamber and do.
Here we get to use the word intimacy. We want intimacy between the piston ring and the cylinder so that there is no room for a third party. So during World War II, the engines on the B-29 bomber, which was used in the Pacific part of the war, had a lot of problems. And the one tool that best predicted disaster was static leak down, because it would tell you you have a valve, an exhaust valve seat that is moved sideways, so you have one point of contact. Everything else is gray. Or the exhaust valve seat has become oval. You have 2 points of contact. Is that a lot better? I don't think so. So they would leak down test those engines, and they'd be able to, the tester would hand the crew chief a sheet telling which cylinders should be changed. And they just pull those cylinders off and put new ones on.
Oh, I had a friend with this tool. What was it called? The motor meter. I think it was called the motor meter. Engine meter. It was a compression tester that had a little trace. You put a piece of paper in it, and you do your compression test. And it would swing a little pen.
Yeah.
And it was great. Oh my gosh, it was great. So you put the little card in. I just loved using it. And you went 1, 2, 3, 4, 5, 6, 7, 8. I'd use it on a Cadillac 429, 1964. When they moved the accessories to the front, they put the distributor in the front, because on previous models on the 390 it was at the rear. They did a bunch of improvements on the 64, including a turbo hydromatic 400 first year for that long-lived, wonderful automatic transmission. But the Motormatic, and I had great compression. Yeah, whatever it was, 140, 140, 138, 70. Oh. And I still have that piece of paper in my Cadillac file, even though I sold the car forever ago.
Sure.
But just that weak ashtray.
So the bottom line here is, it sounds boring working on sealing, piston to cylinder sealing, but it is actually supremely important, because what's the point of flowing a lot of intake CFM, flowing a lot of exhaust CFM, having a high compression ratio, if you're just letting the compression pressure piss away, because the springs aren't sealing against the cylinder wall. Criminal.
No, it's not for everyone, but for those of whom it's for, it's really for.
And also, it's nice to see others doing it and not have to do it yourself.
Yes. It's important. It is. It's just, a lot of the fancy people in engine building kind of, I don't know, self-deprecate a little bit by saying, I'm not that smart. It's just attention to detail. And intelligence is an interesting subject.
It is. Yeah.
Feel, emotion. How does it all work together? How many watts of energy do we use to run this thing anyway?
It's fairly expensive. That's what they tell us in biology, that the brain uses a large fraction of the body's available energy. So sort of like these AI centers, they're putting in gas turbine combined cycle units right and left, talking about having private nuclear power plants to run AI. These are just the crude beginnings of artificial brains. Beginnings.
Yeah, I think if you think about it, bacon or a pork shoulder or a really nice brisket with all its fat content is kind of the uranium of foods, is it not?
Yeah.
Just does lead to deposits, though, combustion deposits.
The old Eskimo gentleman, I know we're not supposed to say Eskimo anymore, but his name was Kisik. And in describing a hunt, he was describing the animal first. He said, talk about fat. Because a nice fat animal ready for the beginning of winter is the ideal for eating, because it gives you maximum calories. If you're hunting every day, if you're trotting behind the sled dogs, you've got to have calories.
Well, it's just, can you give people context as to why you might have been talking
Oh,
to us?
the family went to Alaska in 1952 when I was 10 years old, more or less. And we went to the North Coast.
Oh,
And we were there for a couple of months. And there was a gentleman and his family who had been in Barrow. Barrow, he said, too much movie. So they went back to their fundamentals, and each day he would walk a number of miles to a particular place where he could get water that he liked the taste of to make his tea. And he had sled dogs. They were crazy, which you always hear about them because there they are, staked out. They get food sometimes. And it was an adventure.
Can't imagine. How'd you get there in 1952?
We drove to Fairbanks. We flew from there to Bettelsfield.
But what did you drive to Fairbanks?
A 51 Kaiser.
Oh, yeah.
with what is it? Gold Seal 6, Continental Gold Seal 6.
Yeah.
Side valve, like we started talking about in the 1920s.
It's so interesting because you think about this 1951 car, that's all we had, right? It was a new car. You drive it to Alaska. So people look at me driving around in my 89 like, you drove that here? You know, somewhere out far afield. Yeah. Or the Velocette, I'm riding up Pacific Coast Highway. I left before dawn and I got the Deachin's Big Sur Inn, which is a great place to eat, especially if it was cold. And it's a great place for breakfast, especially for me. And I pull up on my 54 Velocette and I'm getting out and I'm going to eat breakfast. And I'm pulling off, I got my bell staff because it's misty and cold and it was a little rainy, and got my bell staff jacket and I'm all wind blown, take off my helmet. And this guy pulls up in a very fancy Porsche and he gets out of the car and he's fascinated by this old motorcycle. He's like, man, what is that? And I'm like, oh, I tell him what it is. He's like, you rode that here? Where'd you come from? And I'm like, oh, I came down from, LA, Orange County. He's like, what? And it's, it's like 10 years ago. And it's in 1954, it's like 50 plus 50, 60 years.
Yeah.
50 or 60 years old. And there you are using it, but that's what people did. And I've had my problems, don't get me wrong. Anyway, it's just always great to hear like, yeah, of course you had a 51 Kaiser driving to Fairbanks. Carry on.
New car. Yeah.
Yeah.
And we flew by DC-3 to Bettelsfield in the interior, but south of the Brooks Range. And then my dad's friend and sometime author, Bud Helmrichs, came and got us with the Cessna 170. And we flew
Great bush plane.
Yeah, we flew it was on floats at the time. And we flew to the North Coast in that. And flat six. It really looks strange because in that coastal land, it's perfectly flat, and you can look around 360 degrees, and there's no evidence of humanity. Nothing. It's just yourself. Kind of cool.
It is. Yeah, what was that? That was a Continental, I think, in the 170. I think it was a C-145. I think it was a C-145. They used to name the engines by horsepower, but I think it was 300 cubic inches. So now they would call it a different name, like Continentals are usually an O. It's probably an O300.
Yeah, O numbers. Yeah. So that was
they had combustion chambers too, folks. That's why we're talking about them. Well, thanks for listening. That's Inside the Hot Room, and it's where it all begins and ends for us. Really, it's everything around it is all concentrated on.
We compress the gas. It has fuel in it. We ignite it. It adds heat to the gas. Its pressure rises, and then whoosh, we let that gas press the pistons down and spin the crankshaft.
And what an emotion it brings to us for some reason.
Yep.
I think it's worse. I think it's because we associate it with high speed motion, which if you're that kind of person,
Exhilarating.
we find exhilarating
Yes.
and wonderful. Is there a better feeling than clicking into seventh gear? Well, thanks for listening. Yeah, well, thanks for listening. We'll catch you next time on the Cycle World Podcast.